Thanks for coming to the second IJGIS webinar in 2020. Authors of the paper will lead the discussions today. Geography professor Christopher Yanovich, who is also the director for the Center for Spatial Studies at the University of California at Santa Barbara, will give an overview of selected topics on GeoAI, and his co-authors will join him during the Q&A session. We look forward to your questions and comments. Professor Yanovich will introduce his co-authors.
Yeah, sure, Yano. Hello, everyone. My name is Song Gao. I'm an assistant professor in geography at the University of Wisconsin-Madison.
So Grant would have said that he's an assistant professor at McGill University. Inji, do you want to go next?
Hello, everyone. My name is Inji. I'm an assistant professor from the University at Buffalo, the State University of New York. Budu.
Thank you, Jano. Budu Baduri, I'm the only non-academic and non-professor on this panel, and I'm currently the Division Director for Geospatial Science and Human Security at Oak Ridge National Laboratory.
And May already introduced me so nicely, so there's not much more to say. I'm a professor for geoinformatics at University of California, Santa Barbara, and director of the Center for Spatial Study. And we would like to talk about some aspects here of GeoAI that we think are particularly interesting for such a big overview talk. And I will spend roughly 28-ish, 30-ish minutes on that, depending on how far we can move on. We would like to flip this a little bit and also ask questions from you, and I hope you will all nicely play along. Then Song will take over discussing the result of the polls that we ask you to participate, and then finally we are having an open discussion for the last 15 minutes or so. So let's dive right into this part where we hope to get some of your input. There's a link down below, and because we can't post this into the team setting here, Microsoft Team, we hope that May will post the link that you see down there. Otherwise, I'm going to leave it up as long as I hope that you will be able to participate. The question that we have here for you is, what are key enablers for recent progress in GeoAI? And the term recent here is quite important because we are not ignorant of the past of our domain. We know that there has been GeoAI research not only for 10 years, not only for 20 years, but going as far back as to the 80s. So our question is, what created this recent, a peak in interest and also peak in progress in many downstream applications of GeoAI? And while there may be different reasons for this, we would like you to pick from either a change in data cultures and data availability, breakthroughs in methods and architectures, or breakthroughs in hardware like GPUs, supercomputing, and so on and so forth. So I'm going to leave this on for a few more seconds. I hope you either took a screenshot or it appeared in the chat, or you were able to type as quickly as I hope you would. And we are going to discuss this later, so it would be so cool if you play along. So it's probably not a big surprise if you look at the top of the slide set that we went with data cultures for this talk as being one of the key drivers. This isn't because the other parts don't play a smaller role or something like this. It's just that for a broad talk like this, it's easier to make an interesting or thought-provoking statement of the part of data cultures. So this is a slide that I believe is quite powerful. It's not by us, it's from a web page that is called Programmable Web, and it shows you the trends in APIs, application programming interfaces, that they are monitoring since, I believe, 2005. When they started in 2005, there were roughly 100 of those. The last image I found was from 2019, this one here, and it lists more than 20,000 APIs. Keep in mind that these APIs can be from researchers like me, it can be from government laboratories, it can be from, but the vast amount of the APIs that you see here from commercial parties, enterprises, so to speak. If you think about this for a minute, this is as remarkable, I think, as it gets, because it means that companies perceive the risk of their business internals, of their data, of their secret sauce being stolen or used by somebody else to outgrow them as a lower risk than becoming disconnected or not used by others in this new data economy. It's quite striking if you think about this, and clearly 10 years ago, 20 years ago, a chart like this would be unthinkable. And let me try to bring the same story home using another example that works very, very well for me. And I hope it also works well for you. I'm very interested recently in Elon Musk and the way his companies are run, and especially SpaceX. They are, as you may know, really, redesigning or disrupting the spaceflight business and bringing satellites to space by lowering the cost to orbit by, I believe, a full order of magnitude by now. What I really think is so interesting about the way he runs his companies, in particular SpaceX, is that everything plays out in the open. And this is not an accident. It's not that he forget to seal their data set or something like this. You can get in contact with him on Twitter. You can ask him very technical questions about the material that they are using, about the last accident and launching their spaceship, and he will reply to you typically within hours or minutes. You can film and people their site, which is not secret at all, where they built the spaceship, the Starship, and you can see all the stacking going on there. You can fly with drones. You can do all sorts of things and have access to live streams. And what this gives you is a tweet like this by a tiny community, South Padre, that tells you that SpaceX fleet vessel Go Discovery, that's the one that you see at the very bottom of the left, journey to Port Brownsville has paused at Fort Lauderdale. Very high winds and seas are expected for the next several days in the Gulf of Mexico, placing cargo on the lower profile deck at risk of overwash. This may just seem like a tweet, but look what's going on here. We are able to get a picture of the actual vessel that is actually transporting parts of this Starship, right? We can see what we as geoscientists would call a field observation, namely the wind or the weather on the right part of the slide, and then we see vector or the object data, namely IIS, so vessel tracking data, and we see exactly the path that this Go Discovery vessel is taking, and where it stopped, we see the status has stopped, and we can make a prediction about how long it's going to be there. This is not only fascinating because S. Padre and Mary, who's retweeting this, and she is the person who takes many of the ultra zoom pictures of the construction sites, are citizen scientists or citizens. It's also that we have access to all the data. If you are their competitor, I bet you would love that. And if you are the insurance company, I am sure you are monitoring, day and night, Mary taking videos nonstop from the site where you actually see accidents at their construction site happening in real time. So the trade-off here that SpaceX is taking is being radically open to create buzz, to create interest, to create the perception that they are the best and they are able to hire the best people, versus their insurance company seeing all things that go wrong, so to speak, at their site, and there are quite some accidents. So there's of course more to be said about this than just the availability and connectivity of data. There's of course also the fact that data reuse, opportunistic rate data reuse, is the new normal. And I know saying this in 2021 may seem like an odd thing, but we wanted to go back and see where did this start? Because while it may have been normal 10, 20, 30 years ago to reuse, for instance, satellite data, reuse somebody's small collection data, like their biodiversity sample or something like this, was absolutely unthinkable. Or, and this is one of my favorite examples to this day, there's a research group that in 2009, I believe, but I'm not so sure about the date anymore, they realized that there's a ginormous network of these tiny webcams, low quality cams that point somewhere to the street available. Nobody really does anything with them. Image quality is horrible, but they are just good enough so that you can see different pixels, like green pixels. And they said, hey, these webcams, they're distributed all over the United States. Couldn't we use them to track an earlier onset of spring due to a warming climate based on earlier detection of green pixels? So I'm so excited about this kind of research because 20 years ago, there was not a single example of this kind of work. So there's clearly a change going on here. On the downside, and we don't want to sugarcoat this, it also means that there's an uneven distribution of data ownership. To this day, data production and data storage and the value chain of data is still a one-way street. And this also means that the resources to compete, especially in the market for instance, machine learning, are really dwindling to lesser and lesser parties, labs, and especially companies that can still do the work, and which I think is quite concerning. They are also not always being transparent about the data, for instance. Last point, and I'm sure many of you know this, you're not only the data providers, you're also the crowd workers. Every time you fill in one of those captures, like this is a car, this is a bridge, you're actually working for free to train, for instance, Google's object detection. There were even lawsuits about this. I'm not here to judge, but 20 years ago, we would be having a serious discussion about that. And there's another very interesting thing, namely that we accepted, this is sometimes called the fourth paradigm of science, an uncoupling of progress from inside. And that led to a lot of rapid progress in our domain and other domains by us saying we are okay by outperforming baselines, even if we can't yet explain why we are doing better than some baseline. I think this was an interesting and a great idea. And I also think it's quite a dangerous idea, and we may be reaching this tipping point where the greatness of this idea, so to speak, is outperformed by the risk from this idea. Namely, we are seeing more and more diminishing returns from complex architectures that are stacked and stacked and stacked and nested of each other, with the delta that we provide being smaller and smaller. And sometimes it's hard to say, is it a better tuning of hyperparameters, or did we really make scientific progress? And I'm equally guilty as many of you of some of these papers, and I think we need to get serious about them. So I believe that, and this is actually what my colleagues in industry tell me, explainability will be at the forefront of the next push to, understand that this was great for some time, but it's maybe not where we want science and industry to be in like 10 years from now. And finally, and this is to all your graduate students who are listening out there, there's an increasing confusion between data-rich situations and situations that are rich in insight. What I mean by that is that I see more and more often by other students, also by my students, the argument brought up that, yeah, that's a really interesting research topic, maybe it's even of huge importance, but there's not enough data, I can't work on this. Isn't there something more exciting or more data rich that I could be working on? So there's an entire realm of research that is really losing interest, or at least mainstream focus, or our crazy citation bean counting these days, simply because it's small data. And I believe that, or we as authors believe that, that spells trouble, because we are limiting ourselves to what type of questions we are asking based on whether we have enough questions and whether we have enough data to use learning techniques on top of them. So the second big block that we wanted to talk about is this idea of spatially explicit models. So what we wrote in our work is that ideally the application of techniques from artificial intelligence and data science to spatial data in earth and social sciences is not a one-way street. Recent research has shown that spatially explicit models substantially outperform more general models when applied to spatial data. And we have been making this kind of argument many times in our literature, and I know many of you have as well. But it does beg the question, what the heck are spatially explicit models? And when we say they work better or substantially outperform more general models when applied to spatial data, what's the tipping point here? I'm sure you're familiar with the situation that is a general purpose data set, for instance, in our graph applications, and some fraction of it is spatial. This is where most of your data from your research contribution sits. So depending on how the sample looks like, how much spatial data is in that general purpose data set, the better or not so good your results are. Where's the tipping point, but what does it mean, for instance, for showing delta in our research, right? The first point here, or excuse me, the second one, what is the tipping point? I think that's great for our discussions after my brief presentation here. What I would really like to dive in, or in fact we as authors together, is what spatially explicit even mean, right? Interestingly, there isn't so much about this. When we started to look more seriously into this, I believe 4 or 5 years ago, one of the most prominent documents or series of documents by Goodchild and Daniel specified those 4 tests. And if you fulfill just one of them or many, you are in a spatially explicit model. So there's the invariance test, the representation test, the formulation test, the outcome test, and so on. The invariance test, for instance, will say that spatially explicit models are not invariant under relocation. Well, I think these are great questions, and I'm so thankful for them having come up with these tests. But I think we can do better, and we can also quantify how spatially explicit our models are. But let's leave this aside and just dive a little bit into what does this actually mean. Before doing so, let's also briefly talk about the types of data that we are going to encounter on this brief journey. At the beginning of all of this, roughly like 10 or 15 years ago, the big trend was, so to speak, more data, which was called big data at that time. The belief or hope that more data will solve many problems. To some degree, of course, it does. To some degree, we know that it doesn't. And diverse data or heterogeneous data or multimodal, multi-perspective data became, I believe, the next big or important topic. Again, from today's perspective, this may not be controversial at all. When we wrote a paper about data diversity 10 years ago, we were met with quite a backlash from the big data community. So these things, change and do grow. And I believe that after that, what we saw was a move to linked data. It also goes by the name smart data and other, simply because it describes the fact that the data is self-descripting, so to speak. But what fascinates me most about this is that the big data part, so to speak, has or had heavy reliance on an attribute view of data, data that has a heavy reliance on activity between individual observations, for instance. So saying it's the relation that matters, it's the network of meaning that is created, if you like, instead of simply the attributes of, relations, be attributes, to put it very bluntly. And now I believe we are moving into what we are going to term here scope data, totally made up term, and like it or not. Namely, the fact that these data sets and their relations between them should be considered not only on the level of individual observations, so to speak, which is the linked data move, but they also have their own scope, they have their own range of validity in culture, in space, and in time. And if you look at that literature, the first appeal of this kind of thought is really only a few years ago. And in some literature, like, representation learning, we see the very, very first papers appearing right now, over the last part of the last 2 or 3 years on this. So things are not always true. Things are true within a certain spatial temporal bound. Or to put it differently, space and time are principles for knowledge organization. What do we mean by that? Well, if we talk briefly about graph data here, which just happens to be my pet peeve or my area of expertise, then we can talk about, typical spatial examples like Los Angeles being 95 miles away of Santa Barbara, directional examples, Los Angeles being to the east of Santa Barbara, topological examples like that Santa Barbara and Los Angeles are both contained in California. And of course, thanks to Egenhofer and colleagues, also about metrically defined topological relations. And we gave them a slight thematic twist here, so to speak, by giving you this Thomas Fire affected Santa Barbara example. But geodata is substantially richer than just those families of data. It's also about the fact that certain statements are temporally scoped. So for instance, you all know that Angeles is known, but only some of you may know that Santa Barbara was actually the Hollywood of the silent movie era. It's Santa Barbara that was very, very well known for the industry, but that's only true until roughly the 20s and relates to an earthquake that also destroyed part of the city. So it's true that Santa Barbara is known for the movie industry, but only up to the 20s. And of course, you can also play this with spatial examples, and then it gets really, really interesting and fascinating. But you can go even more abstract and go away from these A-box, so assertion box examples, to T-box, so terminological examples, and say that there are many definitions of classes like town, city, village, mountain, valley, poverty, and so on. And because all categories are constructed, they're artifacts of human cognition, there are many ways to construct, and we learn to construct depending on culture and regions, time, and so on and so forth. So what a town is and what is legally varies across the US. In fact, for almost all states. In Pennsylvania, there's just one town, everything else is something else. In Utah, I believe you have to have more than 5,000 citizens to switch from town to a city and so on. In California, cities and towns are declared to be the very same thing. So the meaning not only of assertions, but the meaning of classes is spatially and of course also temporally scoped. So usually we would be diving into cities and towns and whatnot examples, but we thought that maybe, we are all sitting in endless Zoom or Microsoft Teams sessions, so maybe a more whimsical example would do for today that will hopefully stick in your minds for quite some time. So let's talk about injustice here, namely the injustice that was done to poor Pluto in 2006, when Pluto was unfairly demoted from the state of planet to a dwarf planet, leading to outrage. So what does it really mean to be a planet? Well, I'm going to start here from the Renaissance. I'm not ignorant of the past, and I know that in the past planets were of course also known, but just for the sake of this example, during the time of Renaissance, we had 6 planets. So the definition, if you look at it from a categorical, so from an extensional perspective of planets, would include 6 members. So the Renaissance would be the temporal scoping here, and I put this little star symbol to remind me and you that this is a very Western perspective, and by not including different views on what planets are, I'm not ignorant, I'm just making a simple example here. So then in the 19th century, we learned more about planets and moons, and our ways to observe improved, and there were 11 planets. Just a few years later, we understood to tell apart moons and planets and so on and so forth, reduced the count to 8. This stayed like this until 1930, where 2 big discoveries around that time were made. The first one was, actually there may be other solar systems and they may have other planets even though we can't observe them yet. So we had to spatially scope what it means to be a planet for the first time by saying what we mean by planets now, for the sake of this example, planets in our solar system. That's a very big temporal scope, spatial scope, but it is a spatial scope on the semantics of planets, right? And of course, there's a temporal scope, namely until 2006. We also discovered in that time in the 30s Pluto, so now we have planets. And then came this day in 2006, where the International Astronomers Union, I believe that's the name, decided that they would change the definition of what constitutes a planet, like, clearing the orbit around it and whatnot. And this implied promoting Pluto to a dwarf planet together with a couple of other ones. So we were back to 8 planets, so to speak. Well, but not so fast. I told you that categories like constructed, and if they're really constructed, and if they're really constructed, there should be like adaptive radiation going on, right? Like that. And there is. A year later, because the outcry wouldn't settle, New Mexico declared by law, this is no joke, this is legal, that whenever Pluto passes over the nightly sky of New Mexico, it indeed is, and forever, I'm quoting, and forever will be a planet. So it's that there's a new temporal scoping from 2007 ongoing, but now we are radiating into also a spatial scoping, namely planets differ by definition. In New Mexico, there are 9, for many of us, there are 8. And of course, if there's a radiation, you would expect this to happen multiple times. The very same 2009 in slightly different conditions, slightly different time of the day, so to speak, but in some parts of the night, Pluto is also a planet over the sky of Illinois. If you wonder why, the person who discovered Pluto was born in Illinois and worked most of his life in New Mexico. That's why. This example is entertaining. It also points to a larger problem that many communities ignore, and where we as authors believe our role is really important as experts of all things spatial temporal, is not only understanding these scopings and understanding geodata, but also pushing the fact that to this day almost all reasoning that we see is strictly monotonic. So the idea of you adding assertions like I did here going through, but decreasing inferences is simply not a thing, right? It's not an allowable, it's not an even implementable operation. Of course, there is some work of non-monotonic reasoning, but it's just a tiny part of the literature. And as we are now all moving to understanding that things are temporally scoped and things are spatially scoped. This will become on the forefront, I believe, of reasoning services or inferential services in the future. Continuing our point here about what spatial explicit means and how far it really reaches into all sorts of domains. Let's go away from the of declarative knowledge, so knowledge engineering, so to speak, with us defining what planets are, to a case of learning representations bottom up. And before we dive into this, about a case of social sensing, so the idea of trying to define the meaning of terms like, for instance, restaurants or musea or schools, bottom up by observing when do people go there, how are these places geographically distributed, what do people write in news or social media about these places, and then try to come up with representations that are driven by data of human behavior. And we did for a couple of years. Song and Grant and Indy will have a lot to report about this, but then we realized we haven't only shown that places have a temporal component, places of course have a spatial component, but places also have a linguistic component, like there's a highly geographically distributed density surface of all terms, for instance, in the English language. And Ben Adams, I think, is the leading authority on this. Check out his Franken Place work, and together with Grant McKenzie, of course. We also realized that maybe we can use this for social good, right? We could develop a service like this and publish a few years ago, where the service will look at your tweets, like looking for tacos and margaritas tonight, and then understand that if you post this in this specific region at this specific time, this short tweet maybe all it needs to hyperlocate you down to the specific restaurant or sports bar where you went. And we were able to show this, and also able to show that if you just change the wording a tiny little bit, or, and Grant can correct me if I'm wrong, submit the tweet half an hour later, you change the entropy pattern in a way that your tweet is hidden, so to speak, by the masses, and you can't be precisely geolocated. I believe in this case, the system would recommend like tweet this half an hour later or something like this, and it wouldn't be obvious anymore where you are. So language is of course highly spatial, right? And the usage of language in relation to places is highly spatial temporal as well. So now up to the part of learning, because these days I guess GeoAI is often confused for just GeoML, so to speak. What we were also interested in as authors represented on this panel here is trying to showcase many of the techniques that are coming over to us from other domains like NLP are unaware or even ignorant of the fact that geographic space is not one-dimensional and doesn't consist of unit distances, so to speak. So at that time, this is like 4 or 5 years ago now, things like word-to-vec as an embedding technique, as a technique to turn one hot vector, so to speak, into a lower dimensionally embedding, were very hot. And people started to use them also for embeddings of geographic feature types, like place types. And we showed, or wanted to show, that you can substantially better, even if you do a very small step by just being very smart about how you resample the data, so to speak, or unevenly sample the data, by saying we can follow the distributional semantics approach, namely that you should know a word by the company it keeps, and apply this to place types, but not be ignorant, so to speak, of the properties of geographic space. What we did is we took for every type of place from, I believe, 570 place types, a center place for training, and then we created concept distance bands, and oversimplifying here count their frequency and popularity. Why this was quite powerful is for multiple reasons. First of all, we were able to show a very substantial delta compared to the existing literature. So even tiny approaches like essentially modeling a variogram, so to speak, make quite dramatic differences. We were also able to make some interesting discoveries on our own, namely that you would naively believe, based on omnipresence of Tobolow's first law in all of our minds, that the places of certain types nearby your individual place of the type that you would like to learn about would be the most influential one, and then it would decay the further you go out, the larger those distance bins grow. And of course, they are area normalized, right? But that's actually not the case. So it's true for many places that if you would like to know the place type, you need to know the neighbors. So if you no, all the neighbors are pubs. The place that you would like to guess is most likely a nightclub or something like this, or another pub. But there are also place types where the opposite holds true, where to know what this place type is, it's very helpful to know what does not appear over the next miles, or what does appear only at the periphery. School examples in jails, for instance. Right? It's hard to say what's always co-located with a school, but it's easy to say that schools and jails typically aren't. By the way, we were also told just recently that the POI team at Baidu Maps is looking into this approach and having some nice results of this. And it's these examples where simple often shows large delta when it comes to spatially explicit, and you get diminishing returns. If you would start to say, well, why concentric circles make scan ellipsoids, what about local density and so on. Super interesting, but maybe not as powerful as the dramatic approach. By the way, there's some really interesting relations here between this entire embedded literature and conceptual spaces as studied by Gerd Forsen in our community, Martin Raubert. I think these are largely unexplored to this day. So for the last 2 or 3 minutes before I'm out of time, let's talk about another example of what it means for us to be spatially explicit. Last year, Inge and friends published a paper about geoparsing, and they come to the slightly provocative conclusion by saying, and so on and so on and so on, and the parsing well-formatted text referring to prominent place instances could be considered as solved. And that, when Inge presented us, that led to quite with us and him and of course what saves the sentence is to say prominent, right? But even for the prominent, let's have a discussion here. So if you look at OpenCalais, which is one of the most advanced systems to parse out places, people, companies, relations, and so on out of text, it will take you as a human reader under 10 seconds to understand that Vienna and Parkersburg host a Christmas parade, blah, 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 in Ohio Valley, and that's probably some Vienna in Ohio, or if Ohio Valley would be somewhere else, at least in the United States. OpenCalais perfectly believes this is Vienna, Austria. So how does this match with Inge's statement below? Because he certainly did his job in doing careful and very good research. So what explains this disconnect? Well, we started to ask ourselves, is geoparsing really solved, or is the evaluation simply biased to a degree where it appears solved? So what do we have in mind here? Well, it turns out that even things like difficulty, so the idea of difficulty, is a spatial concept. Because look, if you look towards the very left side on the map there, this is the distribution of places in one of the more prominent evaluation data sets. There are others, and some have even more biased geographic coverage. So when we mean we are getting good, or our evaluations show that we are doing great on geoparsing, what we mean is we are doing great on, in the United States and Europe and, some other places, right? But the level of difficulty, and this is what's also varies geographically. So difficulty is really in itself a spatial concept that needs to be taken into account in evaluations. The map here in the middle is all places that are cities, so not just all places, but all places that are cities called San Jose. And of course, if you know the history of Spain, you will not be surprised to find them in the Philippines and all over the Americas. So if you mismatch your first ranked choice for a San Jose, you can be more than 10,000 kilometers off. Right? On the other hand, if your sample or your training or your test data contains Petershagen, this is the one on the very right, well, good for you, because you can only be off not in the 300 cases of San Jose, but only in 5 cases. And I have even better news for you. You can only be off by, let's say, 1,000 miles in the very worst case. I know that you know this. I know that this may not surprise you because you're a GIS scientist. Those evaluation metrics that compare geoparsers and so many other systems are totally ignorant of these facts, right? And of course, history matters, because places with a longer history, and I should maybe say with a longer history of conflict, are more likely to have way more toponyms, like for instance in Europe or the Middle East and so on. And this is a graphic that luckily my students were able to get to me right in time for the talk. So thanks to them, which has a regionalized version, so to speak, by those hexagons of the maximum possible error in regions of the world as covered by the GeoVirus dataset that I showed you before, used for geoparsing. And you can clearly see that the level of difficulty varies greatly. So in some places you can't be off that much, in others you can be off greatly, of course, for historical reasons, for instance, in Australia. And of course, it shows again the issue of uneven coverage. So spatially explicit, or space is everywhere, and it even trickles down to how we should evaluate. That's, I guess, what we are trying to say. But it's close here with asking you again. Many years ago, 22 years or 23 years ago, we had this moonshot, so this big idea that was supposed to propel us to new heights and create a new community and make our domain easily explainable to others of the digital earth. And here the idea was to have this representation of the entire globe connected by all sorts of data layers, and you being able to ask questions across data layers about almost everything on the surface of the earth. We would love to discuss with you whether this has been a good idea, whether it's still active, whether it was a good idea to have such a moonshot, but it's undeniable that it was easy to talk about this idea, that communities formed around this idea. So we thought, maybe we can propose another one. Maybe it's time for a new moonshot. So here we introduced the artificial analyst, so to speak. And the idea is quite simple. Can we create an artificial GIS that for simple problems solves a domain-specific Turing test by 2030, by which we mean, can we develop an AI GIS analyst that passes a domain-specific Turing test by 2030? So can we design a software agent that takes a user's GIS-related domain question about insolation, for instance, into account, understands how to gather the required data, how to analyze the data, so the sequence of operations, so to, then how to represent form like on a map inside. That's the Turing part here, that you couldn't distinguish whether this was an entry-level GIS analyst or whether this was an artificial analyst. We have our thoughts on both whether this can be done by 2030 and what the major roadblocks would be, but of course we would like to flip the script on you and hear from you. So I'm going to leave the URL here, and I wanted to talk for 30 minutes. I'm in minutes 33 now, so I guess it's time for me to shut up and hear first from Song about the results of our little poll here, and I play nicely along, and then dive into a discussion with you guys. Thank you so much for listening.
Well, thank you, Jano. I don't know whether you will be able to access the link through our team channel directly, but if not, I apologize, and maybe you can just type in the link on the slide. Jano, do you want to put on the slide again so that people won't forget the URL?
Oh, absolutely. I'm happy to do so. Do you see it again?
Yes, thank you. So let's go around to see comments from your co-authors. Just a quick comments about your thoughts or some points that you want to add to Jano's presentation. Song?
Hi, May. Hi, everyone. I think I don't have additional comments. I just maybe wait for 2 or 3 minutes when people's survey coming. I can share my screen. Maybe at the same time, if some pop-up questions and that maybe audience can post, and ours we can answer that.
Thank you. Injesh, who?
Hi, May. Yeah, me too. So I think maybe we can first see the survey results, and then we can discuss in the Q&A sessions.
Okay, thank you. Budu?
I'm good with.
All right, good. Grant? Grant?
Yeah, I think Grant had some difficulty previously in unmuting himself, so I'm not sure if he is connected now.
All right.
Yeah, maybe I can share the screen now, I think.
Okay, can you do that?
Yeah, we have a sufficient result. So can everyone see my screen about the first result?
Yes.
Yes.
Okay, yeah. So for the question one, we ask what are the key enabler of recent progress in GeoAI, and we got the most answers from the changing in culture, data in culture, and which is Jano talk a lot. And also second one is a breakthrough in methods and architectures. I would like to share that recently, because we keep update about GI science literature, especially on IJGIS. There are about at least 3 articles about the geographically weighted artificial neural network, which actually are very interesting. I think that's also belong to the recent advances in the methods about the spatially explicit AI method. And lastly, is about the hardware advancement. We know that for training the deep learning models, and we need maybe some of the GPU or high performance computing support. Otherwise, it will take a very long. And the second, survey, we ask you about the artificial AI GIS analysis for passing the domain-specific Turing test. We got mostly at 2030. So seems that we are very optimistic, GIS scientists. Kudos. And to do that, most of the people actually think the most important steps, top 2 are, first of all, understanding the user's intended question, and also understanding what analysis or the sequence analysis to perform. So that is my short report. I'm going to stop sharing and welcome your thoughts.
Thank you. Any questions from the audience? It's time to raise your hands, or if somehow your raised hand is not there, you can email me, then I can call your name. Okay, so I think that I might have caused some problems with the technology. I need to get some more trainings. This is awful. But a question from me, since I take the opportunity here. I think that one of the most important points that you mentioned here is really spatially explicit, what it means and how we should do with it. Currently, there are a lot of IJGIS manuscripts that they use geospatial data, apply neural network, especially CNN, to do a lot of analysis. And it's really not much into spatial explicit because the data itself really doesn't have much added spatial meaning to it. Other than pixels or other than point-based data. Do you see that there are a lot of eagerness to just try to get the data, apply the method to the data rather than to think through the usefulness of artificial intelligence to advance GI science? And then if for a new student coming to the GI science, how do we guide them through thinking about spatial explicit? And any takers?
Yeah, I can take this, but I think Inji, do you want to go first?
Yeah. So yeah, I think for one paper to be published in our domain flagship journal, IJGIS, it must make some innovative contributions. So I guess from my perspective, I see 2 possible ways that those innovations can be made. One is that, like Jano has showed, we can develop spatially explicit models. Basically, we look into those deep learning models, we open them up, and then we try to add some of these spatial components there, right? So try to explicitly represent spatial concepts such as spatial weights, spatial interactions. And by opening these models and then try to add those spatial representations, we eventually improve the performance of those models and to better answer geographical questions. This is more of the first approach, spatially explicit models, but it also requires that the researchers really to have a deep understanding on these models. Another approach I also see also involve quite some innovations is that we can try this geospatial feature engineering approach, namely in which we do not directly open the models. So we still try to use these models, for example, deep neural networks, random forest by itself. But what we try to do is to include our geographic knowledge and by creatively representing them as input features. So you know, for machine learning models, input features is a major input for the model itself. So how can we actively, creatively generate those geospatial features, even for deep learning models? How can we include those geospatial features by, for example, using spatial relations, right? I think our GIS can play a very important role in generating those geospatial features by looking at, for example, the distance between points to other geographic features, by looking at the elevations, population density at these locations. By doing those GIS operations, we actually innovatively add a lot of new geographic features there. In that case, even though we are not directly improving the model itself, we are still adding new knowledge. We are still including our geographic expertise to improve the performance of these models on these geographic questions and help us better understand our social and natural phenomena. That's my take.
Thank you, Yijing. Yano?
Well, of course, I concur with Injay, but a few things to add here. Over the past years, as I said, we have shown for multiple tasks, for multiple downstream tasks, and for multiple domains, that spatially explicit models do make a dramatic difference. Sometimes, even up to like 300% in delta. So I think that posting this or submitting this to IJGIS is, so to speak, a little bit of missing the point, because ideally this kind of work would be submitted to other domains or to the core machine learning communities, for instance, right? So my student Geng Cheng works, for instance, on location embeddings, which are relevant to applications, for instance, in studying biodiversity, and he places his papers in conferences on, for instance, representation learning quite successfully. Or my student Ling Shi works on temporal embeddings and is publishing this literature also in the computer science literature very successfully. So I believe that our task is to make sure that this doesn't end up as a one-way street, that there's progress in AI or, and this is by the same, I'm more of a knowledge engineer, right? And then we take it and we apply it to geodata. This is good and this is necessary, but we have so much more to offer, and this is what the talk was supposed to show. The very idea of evaluation is a spatial temporal concept, right? Data is spatial temporal in more than just latitudes and longitudes, right? Many applications that may not look like they are spatially, like linguistics, are deeply spatial. We need to push on the data side, data sets that spatial richness that specific that use more than just location, so their delta in our community. We all know the delta here, but in other communities.
Yes, thank you, Yano. We have a question from Christopher Clamanon. Christopher, can you do you want to ask online? Can you hear us?
Can you hear me, Jana?
Yes. Yes.
Yeah, I have a question regarding the Turing test, which is a difficult one, especially if we think that GIS is made of complex information. I was thinking not about a question, but a sort of collaborative process between a question, a large question, and a GIS AI agent, where the question will be a sort of collaborative process between the system, an intelligent system, and the user. So the question will be, it's a difficult challenge, having a sort of Turing, not a question, but a sort of process where the user will not see the difference between a real agent that will deal with the question or the GIS intelligence system that will deal with the question.
First of all, great from you and wonderful question. And indeed, this is what we have in mind. But for the moonshot, we wanted to go even broader. So intelligent analyst, the one that we briefly described in the paper and here, would of course do what you just said, would be able to do a Q&A style, like your Siri on your phone or whatnot for geo-specifications. And when it comes to this, we are getting really quite close at shockingly high speed for simple questions, right? So I think that the idea that you could ask a simple GIS analytics question and the intelligent agent would understand the question, grab the ArcGIS or whatnot toolbox, grab the data from a web feature service and whatnot, do their magic, and then return, let's say, a map. I think it's quite optimistic, and I agree that it's quite a difficult challenge. I wouldn't be too surprised if by 2030, 2035, we have first examples of these systems. What's your take, folks?
Oh, okay, I think that we should stay optimistic. It's always feel hopeful, and then we can stimulate young talents to really contribute to the field. So I do agree with Jano that we probably don't want to set limits, and then more ambitious and optimistic thinking might push us further than we might have expected. And there's another question from Zhang Changchang from in China. And he asked that what will be the most difficult parts of research in GeoAI, and what are the data policy or confidence issues related to GeoAI that we need to be aware of? And I think that's the key two parts of his question. One is the most difficult part. I think it should be intellectually difficult part to get into GeoAI or really make progress in GeoAI. And the second is data policy and confidence trust issue. Any takers?
I can try.
Yeah,
I can take a try. First of all, for the first question, actually, this is actually an excellent question. Even for within my group and also others, I think that first of all, in order to contribute to the field, we need to actually learn a lot of multidisciplinary knowledge, especially from different intersecting domains. I think that is the first challenge. The second challenge is because you really need to, as Jano said and others said, when we try to develop new methods or even new theory, and that need a really intellectual advancement. And to do that, you need to me, I think that we need to have a good understanding from all aspects, but it's very challenging to do that. So we have to narrow down to, for example, I'm very interested in doing the modeling of spatial interaction, and then I need to understand this field and also trying to maybe integrate some latest graph-based neural networks, which is appropriate to model the spatial interactions. And I think this is an example that when we try to make advancement in the field, we need to understand multiple domains. And regarding the confidence, that's back into one of the challenges. Like in the AI, especially for the computer vision or image-based, they have a well-known and accumulated image net. But for us, in our geospatial domain, we may not have access to such ginormous label data or have maybe biased data samples in the training the models. So I think in that sense, this is why we need to maybe put more efforts for those data sharing and also replicability or reproducibility when we publishing the article. I think that will also increase the confidence when we integrate those GeoAI models. So that's my answers.
Well, thank you. Grant, you have been your research have extensively used a lot of POI data. And one of the easy entry point for people to look for GeoAI research is really take advantage of availability of POI data and social media data like Twitter's, and then maybe somehow relate them geographically. But do you see any issues or any opportunities that to get somebody quickly get into this field? What do they need to prepare themselves to better utilize POI data and other social media data? Oh, I forget. Your microphone is having problems. So I think, Song, you use a lot of social media data and POI data too, right?
Yes. So for the POI data, for a lot of our work, actually also rely on some of those enterprise their open data challenges. I think that is a good source, but we also actively collect the social media data from like Twitter or other platforms when they mention places, because places have a multiple representations format. Could be place names, could also be those specific points of interest. So we hope that those POI database accumulation and also multi-source POI data would be more available. And because one interesting direction we'd like to test is actually about the generatability or other scalability issue when we do the model development.
Yes, Jano.
If I would be Grant here, and I hope Grant isn't going to be angry at me later on, he would probably say that we also have to understand these POI data sets, that why we want to learn from them, and of course Song and G and Grant have contributed greatly to this literature, we also need to understand their variability over space and cultures, right? So learning and understanding what a type of place means in one part of the world doesn't necessarily equate to understanding what it means, what it implies for people interact with it in another place of the world. And of course Song and Grant published extensively on both the spatial and temporal aspects on this. In general, I believe that my main worry with this very rapid progress that we see now is, when I talked about this data richness, is that these technologies are normative technologies, but the most interesting part, societal, cultural, and also where we want society to go, is on those fringes of these kind of normal distributions. How do we incorporate spatial heterogeneity, so to speak, more in these? How do we incorporate individual differences? How do we incorporate the fact that conceptualizations vary by regions and so forth, right? So I think these are very big challenges for the future.
Very well. I look at the time, we actually go over it a little bit. So a final thought before then we will end this webinar. Anybody? All right.
Yeah, we do need this together as a community. Yeah.
Yes. So just a little bit context in IJGIS. Now we receive probably 80% of the manuscripts have some flavor of GeoAI, either machine learning, classification, big data, that nature. But I hope that with a lot of conversations in the field, we can actually move beyond just apply the existing computer software like a Skilling or like a Google Coursera or other existing softwares, and then apply the geospatial data and then try to show there is a cluster. It's really go beyond to what Jano say. It's not just reaching data or reaching algorithm, but reaching insight. I think what reaching insight is really the key for innovation and advancement in GI science. And I thank you everybody for coming to the webinar, and especially the presenters, and you have given us a lot of food for thought.
Thanks so
Thank
much
you.
for coming to our talk. Bye-bye. Have a wonderful rest of your day and stay safe.
Thank you. Take care. Our next webinar will feature the paper on real-time GIS for smart cities. Professors Wenwen Li, Michael Batty, and Michael Goodchild will give us short presentations individually and join discussions with the participants after. The paper is freely available at IJGIS website. We look forward to your participation in March.